Hello. Tonight we want to continue our notes on Newton's laws of motion and the relationship between force, mass, and acceleration. So to do this, I'm going to share my whiteboard with you all and continue with our notes. So remember that Newton's laws are showing us a relationship between force, mass, and acceleration. So before I continue, I want to write down more formal definitions of each one of these and the variables that we use to take a look at them. So number one, force is written with a capital F, right? So that's our variable we use to represent force. And by definition, a force is a push or a pull. We measured in units of newtons. Okay. It is a push or a pull. Very simple. So F is the variable representing force measured in units of newtons, by definition, a push or a pull. Lowercase m is mass. And actually, I want to add up here to your force, it's a vector quantity. So I'll explain that after we're done with our variables. So m is mass, units of kilograms. So these are the base units in the metric system, the SI system. So every time we want to use these variables in any of our equations, these are your basic units, newtons and a kilogram. Basically, mass is the amount of matter making up an object. Whoops. As I said today, it is a measure of inertia. So a measure of inertia, it is a scalar quantity. Our third variable that Newton relates together, force, mass, and acceleration. A for acceleration, lowercase a. Acceleration, unit of meters per second per second. So an acceleration is a meter per second squared. Often abbreviated ms squared. Like that. The definition of acceleration is the rate of change in velocity. How quickly are you changing your velocity? So the question today was, how do we move an object or how we don't move an object? So just because an object is moving doesn't mean it is accelerating. If it's moving with a constant velocity, then there is no change in that velocity, and we would have it has no acceleration. And that's what he was talking about in his first role, law of inertia. An object will maintain its state of motion. So if it is moving, it'll continue to move at that same speed, at that same velocity, unless there's an outside unbalanced force. If it is at rest, which means velocity is 0, acceleration is 0, it will also maintain that state of motion unless there's an outside unbalanced force. But in order for the force to act, there must be mass. When an outside unbalanced force acts, it will cause an acceleration. So the last thing to note here with acceleration is that it is also a vector quantity. Okay. So what do we mean by a vector and a scalar? Okay. So let's define these. So this is just some vocabulary that I need you to be familiar with to better understand when we get to Newton's second law. So a vector quantity has magnitude, which is how much, and direction, which is which way. Okay. Whereas a scalar quantity, so a vector quantity, has magnitude only. We're only worried about how much it is. There is no direction to go with that. So let's talk about scalar quantities first. Examples of that in your world would be your age. Your age is just a number, right? There is no direction that goes with it. It has a magnitude only. The cost of something. If I go to the store and I pay $2 for something, it is just a number that represents a certain quantity. There is no direction up, down, left, right, north, south, or anything that goes with the cost of an item. Time, 2 hours, 30 seconds. Time is just a number as well. That is considered a scalar quantity. Mass, as I said, is a scalar quantity. So it is just how much stuff makes up an object, how much matter does it have. So the bowling ball had a greater mass than the tennis ball, but I don't have to describe a direction to go with the stuff that makes up the bowling ball compared to the tennis ball. So those are some examples. We'll come across some more throughout the year of scalar quantities. But now what's important is this concept of a vector quantity. So this should be familiar for you from physics, if you've had a physics course in the past. Very, very important concept in physics, which is vector quantities. So as we just said right here, it does matter for force, right? Force is a vector quantity. It matters which way I push or pull on something. Velocity is a vector quantity. It matters which way I'm moving. Am I driving north, south, east, west, right? So that is our velocity. Acceleration is a vector quantity. It matters which way I accelerate. Am I putting my brake on or am I putting my gas on? That would matter whether I change my velocity by speeding something up, slowing it down, making it go backwards, changing its direction, and so on. So vector quantity is anything that has magnitude and direction. So if you have to think to yourself, is there direction to go with it? We would consider that a vector quantity. Does it matter that it doesn't have direction? That's a scalar quantity. Okay. So here's some vocabulary for tonight. We have force, mass, acceleration, 2 of which are vector quantities. 1 is a scalar quantity. So how, when I am writing these, do I recognize that they are vector quantities? So if we go back to our notes, when they are a vector quantity, we symbolize that by putting a half arrow up above the variable. So these 2 would have that arrow representing a vector quantity. Sometimes in written text, instead of the arrow, you'll see a bold face. So instead, maybe I would write my force as if it was a bold-faced quantity, right? But that takes a little bit of time to color everything in and make it stick out as a bold quantity. So instead we use that little arrow that's above it. But if you are reading some text and you see bold-faced quantities represented, variables that are represented, that means that they are a vector quantity, and in analyzing them, you want to consider their direction. All right, so to complete your notes, and then tomorrow in class, we're going to practice all this and pay it, go back through and talk about what is that action, reaction, law of inertia, second law. Let me write for you Newton's second law. Okay, so the one that we left out today was the second law. The reason I left that out is I didn't want to rush through it too quickly. So the second law is often called, or it's just an equation. So as I wrote today, it's an equation showing the mathematical relationship between force, mass, and acceleration. So using the symbols that we just went over, Newton's second law is written as force equals mass times acceleration. We have to add some things to that. Force is a vector quantity. Acceleration is a vector quantity. In our world, there are many, many, many forces. So we also have to add this word net, or sometimes you will see the equation written as F equals ma, vector symbols, and you will see the mathematical symbol sigma representing sum of. So these two things mean the same thing. They mean total or add up. So sigma, sum of, add up all your forces acting on an object, and then you can determine its mass times its acceleration. So an equation very simply written like this says so much. It's one of the most important equations in physics and will be one of the most important equations as we study this mechanics unit of objects in motion or not in motion in our structures. So some important things here, the relationship that this is telling us, as we saw in the first relationship with the law of inertia, as mass increases, right, acceleration decreases for a constant force. What that means is if I push on my tennis ball, it will have a greater acceleration because there's an inverse relationship between acceleration and mass compared to the bowling ball. So if I have two masses, one high, one low, and I apply the same force to them, the one with the lower mass is going to accelerate more. There's an inverse relationship between mass and acceleration under constant force. At the same time, there's a direct relationship. So we would say as force increases, acceleration increases for constant mass. So this is showing a direct relationship between acceleration and force. Whereas up here, this is showing an inverse both equations are showing the same thing. I'm just writing them in different places, but this shows you an inverse relationship between mass and acceleration. So we have an inverse relationship. And that is Newton's second law. So we're going to spend time this week is talking about what is this? What is this summation? What is the net? What types of forces can I have in our world? How do I evaluate the forces that are on our structures and what would be there? So in mechanical engineering, this is one of the most important concepts, the concept of force, mass, and acceleration. All right, we will continue with this in tomorrow, talking about force, mass, and acceleration. Have a great evening.